Okay, today I'm going to start a new topic, and it is the plate bending element, and it could be the last topic I'm going to talk in this semester. Also, I will give you the problems of the term project from this element, and it is also the announcement for the how do I grade for the final exam. And actually, we do not have the final exam, and you need to finish a term project. And actually, in my opinion, it is not actually so big as a term project. I think it is close to the work you need to do is close to a homework. However, I will name it as the term project. And your final the grade of this semester, I will put more percentage in the midterm exam, and less percentage for the term projects, and also the less percentage for the homeworks. You still can turn in the homework, I think before the June, let's say June 25th. Before the June 25th, you still can turn in the homeworks. Okay, so the topics I'm going to talk about in this lesson, which is the plate bending element. Okay, the plate bending element, they are developed to solve the plate bending problems or the plate bending structural models. And we know the problems where sometimes the practical problems can be simulated by some structural models, but the structural model means we have some kinds of the simplified assumptions, and for those simplified assumptions, they are not the reality. They are just something for the assumed by the structural models. For those structural models, we will try to solve the problems. And the finite element method, which is a suitable method to solve almost all kinds of the structural models. And if we use the finite element method to solve the structural models, we will create the corresponding elements which can be used to solve the problems. Okay, so whenever I mentioned if we say this one is the plate bending element, it means that's the element created to solve the plate bending problems. Okay, so what kind of problems they can be named as the plate bending problems? First, the geometry, which is a thin plate. The geometry of the plate bending problems, it must be a thin plate. So if I mention it is a thin, so it means the thickness of the plate compared to the dimensions on the plane, the thickness is relatively a much small dimension compared to the dimensions on the plate. Okay, so that's the geometric character for the plate bending problems. So the thickness is a much smaller dimension, and the loadings. The loadings considered for the plate bending element they are always perpendicular to the plate. Okay, compared to the plane stress problems. The plane stress problems also, which is created for a thin plate, but for the plane stress problems, consider the loading, they are always on the same plane. But if we say it is a plate bending problems, the geometry which is similar, it is for the thin plate problems. But if we say it is a plate bending problems, the applied loading which must be perpendicular to the plate. Okay, so that's the difference between these two models. Okay, so for the plate bending problems, what kind of the internal force or the internal stress we need to consider. For these considerations, we can compare if it is a slender element, sometimes we can use different structural models, and for example, we can use the so-called the cable structural model. If we consider it if the problems is assumed as the cable structural model, the cable structural model, you can say the moment of inertia, the moment of inertia is related to the bending stiffness. You can say the I value, the moment of inertia. If this structure is assumed as a cable structure, you can say the moment of inertia which is close to zero. So it is you can imagine a paper. A paper is which is so thin. It is so easy to bend the paper. So for such kind of the structure, you can use the cable model. Also, we have the beam model. Okay, for the beam model, it is the most common structural model, and for most structural analysis you learned before, they are the methods to solve the beam models or frame model. And for the beam model, you need to solve the bending moment diagram, you need to solve the shear force diagram, and for those kind of the problems. So we need to consider the bending moment. It means the bending stiffness, the moment of inertia. It cannot be so small compared to the cable structural model. For the cable structural model, the bending stiffness, which is assumed to be close to zero. But for the beam model, we need to consider the bending moment, the shear force. So it cannot be the close to zero bending stiffness. So the I values we need to consider. And for the beam models, actually the bending moment and the shear force, they are the major internal force we need to consider. Okay, so for the cable structures, the only possible internal force, which is the axial force along the tangential direction. For the beam elements, the most important internal force, they are the bending moment and the shear force. and it rely on the change of the shear force to resist the vertically applied external loads. Okay, so that's the beam model. If if the thickness of the beam will increase to a certain magnitude, probably we can also use the plane stress models. If we consider it the plane stress models, the thickness, which is usually is larger than the beam model. Compare the beam model with the cable model. The thickness of the beam model is usually larger than the cable structure. Okay, so that's the if we consider a slender element, we could have the cable structure model, the beam model, or the plane stress model. If we consider the plate, which means the significant dimensions, which is not only in one direction, but for the plate structures, the significant dimensions usually they are two-dimensional. So the two dimensions considered for the plate or the in-plane dimensions, both of them they are the significant dimensions. Okay, but compared to the one significant dimensions, we could have the cable model, the beam model. For the two-dimensional, if we got two major dimensions for the plate problems, if we consider only the axial force, then we have the so-called the membrane model. The membrane model also we consider along the two major dimensions, the bending stiffness close to zeros. Then only the force, internal axial force, will be considered, which can be used to resist vertical applied loadings. And for such kind of the structural model, it is the membrane model. Okay, so the membrane model, you can say it is the two-dimensional cable models. If we say the bending stiffness, we do not. If we do not neglect the bending stiffness, also we could have the shear force in two directions. Then it will be the plate bending model. Okay, so you can say the plate bending elements, they are the two-dimensional beam models. Since for the beam model, only the bending moment for the axial directions we need to consider. For the plate bending element, the internal bending, there are two major directions. The bending moment along the x direction, or the bending moment along the y direction. We need to consider the bending moment for two major directions, and also we need to consider the shear force for the two directions. And since we need to consider the bending moment along the two directions, the shear force along the two directions. Also, there is one more internal force, which is the torsional force. The torsional force in the plate, also we need to consider them for the plate bending problems. Okay, I will erase this part. Okay, compared to the one-dimensional models, the plate bending elements, it is the two-dimensional beam models. For the beam models, also we have two different structural models. One you can say which is the slender beam element. The other one you can say which is the deep beam or the say. Okay, one is the slender beam problems. The other one is the deep beam problems. The difference between these two, if the beam is so slender, then you can assume the shear strength, the shear deformations, which is close to zero. That's the assumptions usually we made for the slender beam. But if the beam is deeper, then we need to consider not only the flexural deformation, which is the same as the bending deformation, and but for the deep beam, also we need to consider the shear deformations in the beam. Okay, so the difference between these two is if we use the deep beam model, it means that we need to consider the shear deformations. For the slender beam problems, we consider only the flexural deformation. Move it to the plate bending problems. Also, we have two different models. One is called the thin plate. One model is the thin plate model, and the other one is the thick plate models. And the difference between these two, also it is whether we consider the shear deformations or not. For the thick plate problems, we will consider the shear deformations in the plate. But for the thin plate models, we neglect the shear deformations. Okay. Okay. The element I'm going to introduce, which is the Hermite plate element. The Hermite plate element. The Hermite plate element, which is created by Dr. Hermite. He's an Indian, studied his PhD degree in the United States, and that's the element he created. I think probably it is almost 40 years ago. Okay, that's the type of the element, and for this element, it is the thick plate element. It is a thick plate element, and that's the element. Remember, in the beam element, we have the so-called plane section remain plane. Okay, that's an assumptions used by the beam problems. We say during the deformation of the structures, originally it is a plane sections. After we apply the loading to the structures, for the beam problems, we can assume the plane section remain as a plane, and you can say it is a simplified assumptions since in the practical structures it is hard to always remain as a plane. Okay, so the plane section remain as a plane, which is a simplified assumptions used by the beam problems. And for the plate bending element, we have something, a straight axis. Okay, for the plate problems, there are two directions. We have the rotations, and for such kind of problems, usually we will discuss a straight axis. The straight axis originally, the original direction, which is perpendicular to the plane of the plate. Okay, usually we consider the plane which is the neutral plane of the plate. The neutral plane usually it is also the center of the plate. Okay, so the straight axis originally it is perpendicular to the neutral plane, and after we apply the loadings to the structures, we have the bending and all kinds of the deformations, and the shear deformations, the torsional deformations, and all these it could have all kinds of the deformations due to the internal force in the structures. But originally it is a straight axis. It is also an assumptions. After we apply the loadings to the structures, and if we check the deformed shape, it is assumed for this straight axis, it will remain as a straight axis. If we consider the thin plate problems, you can say the straight axis still perpendicular to the deformed it is still perpendicular to the deformed center plane. Okay, but if we use the thick plate assumptions, which is also the Hermes plate bending element, if we use the thick plate assumptions, then the straight axis will not still normal to the deformed center plane. Okay, so remember we have the assumptions. A straight axis remain as a straight line, and sometimes it is called the Kirchhoff assumptions. Whenever you heard the Kirchhoff assumptions, you know it is related to the a straight line remain as a straight. And also, if we consider the thin plate problems, the straight line is still perpendicular to the deformed center plane. Okay, so that's the basic assumptions. Okay, usually we will define first for the plate bending element. You can say part of the problems we need only the two-dimensional coordinates, and that's which part we can use only the two-dimensional coordinates whenever we need to describe the geometry of the plate. Okay, remember the terminology, the neutral plane or the center plane, okay, which is the, usually it is the center, the located at the center of the thin plate. And usually we will define the XY coordinates on this plane, okay. And whenever we need to describe the geometry of the structures, usually we need only the XY coordinates, since usually we assume the thickness T, which is a constant. Okay, so for most of the structural models, we assume a constant thickness. Then the only thing we need to describe, which is the XY locations. And if we define a set of the XY coordinates on this center plane, then we can describe the location of the nodal points, since whenever we define the XY coordinates for this point, then we can locate the location of this nodal point. Okay, so only the XY coordinates, they are required to define the geometry of the plate. Okay, but the displacement of the problems, and remember for the beam problems, we consider the vertical loadings and the related displacement, which is also related to the vertical direction. For the plate problems, the vertical direction, which is the z directions, the applied loadings, usually they are not only the usually, you can say they are always along the z directions. The applied loadings, it comes from the z direction, and the most important displacements we need to consider, it is also along the z direction. Okay, I will say the displacement along the z direction, the W displacement, it is the most important displacement we need to consider. Also, we have the rotations of the straight axis, and if we since the plate bending element, we need to consider the rotation about the two axes, the x-axis and the y-axis. If we use the two rotations to describe the bending deformation of the plate, then the rotation of the axis will also related to the displacement along the x and y directions, and that's the W. Okay, the z equal to 0 will represent the points on the center plane. So if we consider it is a thin plate problems, usually we assume no matter the z coordinates, the vertical displacement they are always the same. So no matter for the same x and y coordinates, the vertical displacement they are assumed to be the same. Okay, so we have the w of x, y, and the z, which is equal to the w of x, y, and the z equal to 0. This one means for the same x, y, the vertical displacement, we need to consider only the point on the center plane, since the vertical displacement of this point represents all the points for the same x, y, but different z. The vertical displacements they are same, and also we have the okay, so it means if the z equal to 0 for all points on the center plane, we will assume the in-plane displacement for okay, remember, for points on the center plane or for points on the neutral plane, the in-plane displacement they are always equal to zeros. Okay, so that's the remember for the beam problems. For beam problems, and usually for the beam problem, it means that we consider only the vertical loadings. For the beam problems, what will be the horizontal displacement for the neutral axis? All points on the neutral axis, the horizontal displacements, they are equal to zeros. Okay, it means first we do not have the axial loadings. We have only the vertical loading. If we have only the vertical loadings, we will assume all points on the neutral axis, the horizontal displacements, they are always equal to zeros. Okay, for the plate bending elements, if the z equal to 0, the z equal to 0 means the points on the center plane. Okay, for all points on the center planes, we will assume the v equal to 0 and the u equal to zeros, and also v equal to zeros. Okay, that's for the center plane. But for the points on different layers, for points, the z coordinates they are not equal to 0. Then we need to consider the U and the V displacements. Okay. 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 Remember, we will assume the straight axis. Right now, the straight axis, it must be perpendicular to the xy plane. Okay, so the straight axis, which is along the z directions. And for this straight axis, after we apply the loadings to the structures, this axis will rotate about the x-axis. Also, this axis will rotate about the y-axis. Okay, we define the two rotations, theta x and the theta y, and I will use the right thumb. So the theta x means the rotation about the positive x direction. So it will be the rotations in this way. And the theta y, also the right thumb pointed to the positive y directions. Then the rotations will be in this direction. Okay, so that's the theta x and the theta y. And we can use these two rotations to describe the rotations about this of the straight axis Okay, so we have the theta x and the theta y, and also the theta x. Okay, usually we will assume the theta x and the theta y for all points on the neutral plane. So actually they are the Okay, remember the theta x and the theta y, they are defined for points on the neutral plane. So the z coordinates, they are always equal to 0. But for different x, y, for different points on the neutral plane, we could have different theta x and different theta y. So it means the theta x and the theta y, they are functions of the x and the y. Okay, so for different points, we could have different rotations about these two axes. Okay, so for the beam problems, we need to consider the rotations of the center line. But for the plate bending elements, first you need to assume we have a straight axis, and then we have the rotations we have the rotations about the x-axis, the rotations about the x-axis. Also, we have the rotations about the y-axis. Okay, so for any point on this plane, we have two rotations need to consider. They are the theta x and the theta y. Okay. Okay, what will be the u displacement? Okay, the u displacement come from the rotations of the straight axis, and we can say for any point x, y, z in this plate. First, the u displacement equal the u displacement on the center line plus the extra u displacement comes from the rotation of the axis, and we know this one equal to 0, since for the plate bending element we do not consider any in-plane loadings. All the applied loadings must be perpendicular to the plate. So in this case, the UV displacement for all points on the center plane, they are all equal to zeros. So the U, no matter the x and the y, as long as the z equal to 0, the U displacement, it is equal to 0. And also we assume the theta y, you can use the right thumb rule. So the theta y will be the rotations about the y-axis. The rotations about the y-axis will create extra displacement along the x direction. And if the u displacement come from the rotations of the axis, you can expect for points which is compared okay, if we have the rotation of the axis, if we have larger z axis, we have larger displacements. Okay, since that's the rotations, and the extra displacement due to the rotation of the axis. So we need to multiply the z, which is the z, and we have the extra displacement come from the rotation of the axis, and the amount of the displacement which is proportional to the z coordinates. Also, it is proportional to the rotation of the angle. The rotation angle theta y times the z coordinates can give you the u displacements for the points x, y, and the z. Okay, so that's the u displacement. What will be the v displacement? Okay, for the v displacement, but remember if we have the positive theta x, if we have positive theta x, the displacement will be like this one. But also, if we got the positive z direction, the v displacement, which is along the negative y directions, so it is a negative sign. We have a positive sign plus, but for the v displacement, since if we follow the right thumb rule, so you can find that if we have positive theta x, also if we have positive z, then we have negative y displacement. So that's why here should be a negative sign. Okay, that's later I will neglect the z equal to 0, but remember whenever we say the w, usually we just consider the w for z equal to 0, since for different z, the w they are always the same. So whenever we consider the w, the z is always equal to 0. Whenever we consider the theta x, the z equal to 0. The z equal to 0. Okay. Later I will not write z equal to 0 anymore. But remember the w, the theta x, and the theta y, for all these three, they are defined for points on the center plane. Okay, so later, even I didn't write the z equal to 0, but remember the w, theta x, and the theta y, they are defined for points on the center plane. Okay, but I will not write the z equal to 0 again. Okay, that's the displacement functions assumed by the Hermite plate elements. Okay, I think I will take a break here, and I will continue it on the next hour.